In this video, I want to talk about orthogonal matrices. Let's suppose A is an n by n matrix. In order for A to be orthogonal, we need A inverse to be equal to A transpose. In other words, A times A transpose is equal to A transpose A, which is equal to the identity. As an example, let's look at this matrix here. To show it is orthogonal, I'm going to multiply it by its transpose. The transpose is going to take the first row and turn it into the first column. The second row will become the second column. And the third row will become the third column. And as we multiply this, we would have 9 over 49 plus 4 over 49 plus 36 over 49, which ends up being 1. And we can continue to multiply out, and when we do, we will see that we get the identity. So this would be an example of an orthogonal matrix. Let's suppose A is a square n by n matrix. There are a few different ways we can test for orthogonality. So the following things are going to be equivalent. The first is that our given matrix is orthogonal. Next, the row vectors of that matrix will form an orthonormal basis for our n, if A is an n by n matrix. So the rows do actually form an orthonormal basis for our space. And finally, the column vectors of A form an orthonormal basis. So not only do we need the rows to form an orthonormal basis, the columns need to form an orthonormal basis as well. Let's go back to our matrix and show how this works. So let's start with our rows. I will call these R1, R2, and R3. R1 dot R2, that would be 3 times negative 6, so minus 18 over 49. 2 times 3 is 6 over 49, and 6 times 2 is 12 over 49. So we get that that is 0. R1 dot R3, 3 times 2 is 6 over 49. 2 times 6 is 12 over 49, and 6 times negative 3 is minus 18 over 49. Once again, we get 0. R2 dot R3, negative 6 times 2, that would be negative 12 over 49. 3 times 6, that would be 18 over 49. And then 2 times negative 3 is minus 6 over 49. So we do have that the rows are orthogonal. If I try to find the norm of R1, I would get the square root of the first entry squared, so 9 over 49, plus squaring the second entry, 4 over 49, plus squaring the third entry, 36 over 49, which would end up being the square root of 49 over 49, or the square root of 1, which is 1. Similarly, you could check that the norm of 2 and the norm of R3 are both equal to 1. So my rows do form an orthonormal basis. And you can double check, but we could have done this same thing by considering the column vectors rather than the row vectors. Some basic properties of orthogonal matrices. The first, the transpose of an orthogonal matrix is also orthogonal. The inverse of an orthogonal matrix is also orthogonal. This makes sense. If the transpose works, of course the inverse works, since those are the same thing for orthogonal matrices. A product of orthogonal matrices is orthogonal. So if I have more than one orthogonal matrix and I multiply them, it will still be orthogonal. And finally, if A is orthogonal, the determinant of A is equal to 1, or determinant of A is equal to minus 1. And I do want to discuss this one. For A to be orthogonal, we know that A times A transpose needs to be equal to the identity. So we can take the determinant of both sides. We know that the determinant splits up over multiplication, so this is the determinant of A times the determinant of A transpose. The determinant of the identity is 1. Another property discussed when we talked about transpose and determinants is that the determinant of A and the determinant of A transpose are equal. So this is the determinant of A squared. And taking the square root of both sides, I would have the determinant of A is equal to plus or minus 1. Let's look at a quick example. Here's a 2 by 2 matrix that is orthogonal. And I want to look at its determinant. Multiplying this way, we would have square root of 2 over square root of 2 times square root of 2 over 2, minus multiplying this way, root 2 over 2 times negative square root of 2 over 2. This would be 1/2 once we multiply it, minus negative 1/2, or 1. So this is an orthogonal matrix with determinant 1. The last thing I want to look at in this video is a few more things that are equivalent to being orthogonal. So if I have an orthogonal matrix, the norm of A times X is equal to the norm of X for all vectors X in Rn. So we do need to be able to actually multiply AX, but this will work for all valid vectors X. In addition, the dot product AX dot AY is going to be equal to X dot Y for all vectors X and Y such that this multiplication makes sense.